Good day, sir. My name is Sebastian Osuridu, and my co-partner for this project is Ronald Atudankan. And our index numbers are 7409323, and his is 7408123. And this is our CHE 261 project on simulating heat transfer in a pipe using finite difference method in Matlab. Okay, so we are about to explain the setup. We are modeling a pipe that is 10 meters long. We divide it into 50 equally spaced points, giving us a spatial step size of about 0.204 meters. The material has a thermal diffusivity of 0.01 meter square per second, and this tells us how fast heat spreads through the material. So for the time, we use a step of 0.01 seconds and run the simulation for 2 seconds total, which will give us 200 time steps. Okay, so we'll continue with the initial boundary conditions. We start with the entire pipe at a uniform temperature of 300 Kelvin. Then we apply our boundary conditions. Thus, the left end is fixed at 500 K, simulating a heat source, and the right end stays at 300 K, representing a cool or ambient end. These are called the Dirichlet boundary conditions. So for the core simulation loop, this is the heart of the simulation. At every time step, we loop through each interior node, thus every point except the two fixed ends, and we apply this update formula. This explicit FTCS scheme, that's forward time central space, it says the new temperature at a point equals the current temperature plus a correction based on the temperature of its two neighbors. This is the finite difference approximation of the heat equation. After such updates, we reapply boundary conditions to make sure the ends stay fixed. We also save every time step into a matrix called T underscore all, which we will use for the animation. An important thing to mention is numerical stability. For the explicit scheme to work correctly, the Fourier number R, alpha multiplied by a change in the t over the x squared must be less than or equal to zero point 0.5. In our simulation, R works out to approximately 0.0024, well within a stable range. This is why our result doesn't blow up or show any oscillations. So we will start by running the code. This first plot shows the final temperature distribution after 2 seconds. You can see a smooth, non-linear curve dropping from 500K on the left down to 300K on the right. The gradient is steeper near the heated end, which is physically correct. That's where temperature difference is greatest. So the second figure is the animation. Each frame is a snapshot of the temperature profile at a different point in time. You can see the thermal front starting at the left and gradually spreading rightward through the pipe. This is exactly how heat diffusion works in practice. Okay, by t is equal to 2 seconds, the pipe hasn't fully reached a steady state yet. A longer simulation would produce the straight linear profile of pure conduction. Future improvements could include using an implicit scheme like Crank-Nicholson for better efficiency, extending to 2D, or even adding convective boundary conditions for more realistic modeling. Thank you.